All right, so good morning and welcome everyone. I'm Simone Garatti from Politecnico Milano, and I've served as a tutorial chair for this L4DC conference. And I'm really pleased to chair this tutorial, and given it is a plenary session, I take this opportunity to briefly speak about the tutorial process. So as you may know, since the last edition of L4DC, a tutorial session has been introduced with the aim of giving some in-depth presentation of topics that are recognized as of crucial interest for the L4DC community. And this year, the aim was to give 3 tutorials covering the 3 main disciplines that L4DC aims to unite: machine learning, systems and control, and optimization. And we want to emphasize the potential of the synergy of all these areas. And this year, I was very fortunate to secure the availability of exceptional experts of this field. And I think that we have 3 fantastic tutorials on 3 fantastic topics. These are learning under requirements, supervised and reinforcement learning with constraints, which has been organized by Alejandro Ribeiro, Miguel Calvo Fullana, Luis Chamon, and Santiago Paternain. And then we have the tutorial Safety Filters for Control, Concept, Theory, and Practice, organized by Melanie Zeilinger and Claire Tomlin, and Distributionally Robust Optimization for Control, organized by Daniel Kuhn and Wolfram Wiesemann. Okay, and well, I'm really grateful to all these organizers for their enthusiastic response to my invitation. And well, I really would like to thank them, and I invite you to join me in thanking them for their effort and for the invaluable contribution that they're giving to the conference. Okay, today's schedule is rather simple. So in the morning, we have the Distributionally Robust Optimization for Control tutorial. And this is going to finish at 12:30, when we're going to have the lunch break. And after that, we're going to have the other 2 tutorials. In particular, the Learning Under Requirements tutorial will be given in this same room, L1, while instead the tutorial on Safety Filters for Control will be given in the room number L3, which is just next door. And the tutorial session is going to end at 5:30. And after that, I recall you that we're going to have the welcome drinks reception in the main hall of this building. Okay, so I guess that without any further ado, we can now start the first tutorial. So it is my pleasure to introduce you Daniel Kuhn and Wolfram Wiesemann. Daniel Kuhn from APFL in Lausanne, and Wolfram from the Imperial College in London. And both Daniel and Wolfram are exceptional, outstanding researchers, as witnessed by their CVs. And among other things, they are editor-in-chiefs of the 2 most prestigious journals in the field of optimization. And they've been the excellence of their research has been recognized by many prizes and awards. And moreover, above all, they are the pioneers of distributionally robust control, which is a beautiful theory, a beautiful topic, and that's the topic of this tutorial. So please join me in welcoming Daniel and Wolfram from this beautiful tutorial. And guys, whenever you're ready, we can start. USB-C, yeah. This one. Okay, perfect.
Seems to work. Can you hear me in the back? Great, excellent. So thanks a lot, Simone, for the introduction and the kind words. I would like to extend my thanks also on Daniel's behalf to the organizers for organizing this beautiful event. It's great to see so many of you. So the plan for the tutorial this morning is we have two parts. The first part will be about problems with discrete state and action spaces. That will be given by me. And then the second part will look at problems with continuous state and action spaces. If I say that correctly, Daniel looks at me. We'll see, given by Daniel. So this is a tutorial. This is not a seminar. What I would like to try is, even though the room is relatively large, let's try to go through the material at a somewhat slightly more leisurely pace. And if there are any questions, comments, please raise your hand at any time. And I'm very happy. It would be great to make this a little bit more interactive. All right. So much of my part of the tutorial will be about Markov decision processes. Markov decision processes are a very popular paradigm for studying decision-making problems under uncertainty. And for the purposes of my talk, I will consider Markov decision processes as a tuple SA-QPR lambda, where the various objects mean the following things. So first of all, the set S is my finite state space. Think of this as the set of all possible future states of the world that we can find ourselves in. And as you see here, I make a very strong assumption. I assume that this is a finite index set. Likewise, I have the set A of actions that I can take in any of those states. Again, I will make a very strong assumption here that this is a finite set. There are finitely many actions. And without loss of generality, and I can come back to that point later on, without loss of generality, I can assume that every action is applicable in any state. That is possible because we can make actions sufficiently expensive. If you don't like that, just ignore that assumption. You can, some actions may not be applicable in some states. That's perfectly fine. Now, third point, Q, the initial state of my system can either be known deterministically, or it can itself be random. And in either case, I will assume that the initial state is characterized by a probability vector Q, which is the initial state distribution. So think of Q as a vector with one component per state of my Markov decision process. And each component of Q gives me the probability that I start in the respective state. So in particular, all the components are non-negative numbers that add up to 1. Now, arguably, the most important component in a Markov decision process is the transition kernel P, which describes the one-step dynamics of my system. So you can think of P as a function that takes as input the current state S and the action A that we decide to take. And it gives us as output a probability vector over the state space, which gives for each possible successor state S dash the probability that we end up in state S dash if we're in state S and we take action A. Two important things to note here. The first one is that these one-step transitions P that are characterized by P, they only depend on the current state and the current action. This is the so-called Markov property, in honor of Andrei Andreevich Markov, Russian mathematicians that studied these processes a little bit over 100 years ago. And what that means is really the past history of states and actions that we visited does not play a role for the distribution over the next state that we are going to visit. In practice, that often means that the states need to be sufficiently expressive. Everything you need to know for the next state transition needs to be contained in the description of the current state. The other thing to observe here is that I look at problems over discrete, where time evolves in discrete steps. Otherwise, we would not have a transition kernel P, we would have a transition rate function. Now, for each state action pair that we visit, we receive a reward, and we want to maximize the sum of all rewards over time, discounted at a discount factor lambda, reflecting the fact that rewards that we receive later in time are worth less for us than what we receive right now. And then the goal, I'll make this slightly more concrete on the next slide, is to find a policy pi that maximizes the expected total discounted rewards. So what we want to do is we look at an infinite time horizon. We sum up over infinitely many time stages the rewards that we obtain by being in state st. That's a random variable that is governed by the transition kernel P, as well as our policy pi. The rewards that we get for being in state st and applying the action prescribed by our policy. This sum here is guaranteed to converge because of the discounting and the fact that the state and action spaces are finite. It is a random object, so we want to find a policy that maximizes it in expectation. Now I have two more slides of summary of relatively well-known theory, and then I would like to go into some of the more recent research in this field. So why are Markov decision processes so popular? The first, the reason is basically under the assumptions of Markov decision processes, in particular is Markov property, we get a lot of nice properties that allow us to study those processes and that allow us to obtain optimal solutions relatively quickly. So the first property of Markov decision processes has to do with the structure of an optimal policy. In principle, when we solve this problem from the previous slide, this policy pi, we could think of it as being quite complicated. It could, in the most extreme case, be history dependent and randomized. What I mean by that is it could be that the optimal policy needs to differ for every time step t and depend on all the past state and actions that we have visited. That would be very impractical because we want to optimize over an infinite time horizon. The policy would take an infinite amount of space just to be described. At the other extreme, we have policies that are stationary and deterministic. What I mean by that is we have policies that only need to look at a current state, and for each current state, they prescribe us which action to take. And it turns out that in the Markov decision processes from the previous slide, those stationary deterministic policies are actually guaranteed to be optimal. And in some sense, this is the most simple policy class that is still interesting, and they achieve the optimal total expected discounted reward. We will later on also look at stationary and randomized policies, which do not need to recall their history, but they only need to look at the current state, but they might take a randomized action. We will see that this is sometimes necessary for our purposes. Second property of Markov decision processes. Imagine we fix a policy pi, and we're interested in evaluating this expected total discounted reward. At first, this might look like a challenging problem because this is a sum over an infinite time horizon, and we need to take an expectation. Perhaps we need to resort to sampling or something like that. But it turns out that actually the discounted rewards of a fixed policy satisfy the so-called Bellman equations, which means that actually we can get the expected total discounted reward by solving a system of linear equations. Those are given here. In particular, you should read V pi of S as the expected total discounted reward if we're in state S and we keep applying policy pi. And it turns out this expected total discounted reward is simply the one-step reward under policy pi plus the expected future rewards. This is an expectation with respect to the transition kernel, discounted by lambda. Now, this could be in principle solved with any direct method for solving linear equations. I'll show you on the next slide that there is actually a typically much more efficient indirect method to do so. Now, what about optimal policies? So far, I looked at a fixed policy pi. It turns out that the expected total discounted rewards of an optimal policy satisfy a very similar set of equations, the so-called Bellman optimality equations. And those are given here. That's a set of nonlinear equations. V star of S, read it as the expected total discounted reward if we ever happen to be in state S. And from now on, we keep applying the unknown optimal policy. That turns out to be looking very similar to the previous formula. The only difference is that we maximize over all actions. Here it's less clear how we solve this equation system. It's a system of nonlinear equations. In principle, that could be a hard problem. I'll get back to that on the next slide. The only other thing that I want to mention here is, fine, we now know the expected total discounted reward of an optimal policy, but in reality, we're interested in the optimal policy itself. And it turns out that this is easy to obtain from V star, namely the so-called greedy policy is guaranteed to be optimal. So if you have this value to go function V star, which results from the solution of those nonlinear equations, then finding the optimal policy is very easy. When you're in state S, take the action A that maximizes this expression, which is an expression of V star. Okay, so how do we find the expected total discounted reward of an optimal policy and the optimal policy itself? There are at least 3 popular methods. The first one being value iteration. What we do here is we look at Bellman's optimality equation, which is given here from the previous slide. And what we do is we don't know the V star. So what we do is we replace it with an estimate. Let's say instead of V star of S, we take an estimate VI of S. You could start with the estimate of all zeros. That's perfectly fine. And then we keep evaluating those optimality equations to get a refined estimate here. We call this operator that takes a VI as input and that produces a VI plus 1 as output. We often call that the Bellman optimality, the Bellman operator. And it turns out if we keep doing that, we will end up at the optimal expected total discounted reward function, the V star. And the reason for that is because this operator here, the Bellman operator, is a contraction mapping. And then the Banach fixed point theorem guarantees us that we get to the unique solution of the Bellman optimality equations. When people solve MDPs, in my experience, the first algorithm that they tend to implement is indeed value iteration. It's the simplest algorithm to implement, but it turns out oftentimes it's not the most efficient one. So let's look at another algorithm first, and that is policy iteration. What policy iteration does is it looks at the definition of the greedy policy pi star from the previous slide. We don't know pi star, but what we can do is we can replace pi star with an estimate, pi I. Start with any policy you want. Then we evaluate the expected total discounted reward of the policy pi I. That's this function here. And we use the greedy policy with respect to our value function of policy pi I to get to an improved policy pi I plus 1. That is known as policy iteration, and we keep doing that, and again, we are going to be guaranteed to converge to an optimal policy. The problem of policy iteration is we need to evaluate the expected total discounted reward of a fixed policy over and over again. That's more efficient than finding an optimal policy using value iteration, but it's still a challenging task. So it turns out that in practice, what tends to perform best is what is known as modified policy iteration. And what modified policy iteration does is you start with a policy pi I, but rather than computing the exact expected total discounted reward of pi I, you just use a couple of iterations of value iteration to get an estimate for how that value function looks like. And then you conduct a policy improvement step. And you keep repeating the two. The third and last approach that I want to mention is linear programming. In the linear programming approach, we formulate the problem of solving the Bellman optimality equations. We embed that as constraints into an optimization problem. Now this looks like a nonlinear program here, but it turns out due to the monotonicity properties of the Bellman operator, we can replace this equality with a greater than or equal to, because we're minimizing. And then saying that V of S has to be greater than or equal to the maximum over all actions of this expression is the same as just replacing the maximum with a for all actions here. And that's a linear program, and that can be solved in polynomial time using standard solvers. All right, this was just a brief recap of standard textbooks on Markov decision processes. Let me show you one example that will accompany us in the first part of this tutorial, and then I get into some of the more recent research questions in the field. So the example that I want to look at a couple of times is the so-called card pole example, a well-known example from control theory and reinforcement learning. The idea is quite simple. We have a pole that is mounted on top of a card, and we are supposed to balance that pole for as long as possible by only moving the card either to the right or to the left. And we have a limited amount of space on the tracks, which we are not allowed to leave. Now, if we were to formulate this problem as a Markov decision process, which we're going to do, the most natural way to describe the state space of this problem would be to use a subset of R4. Namely, we would have X for the position of the card on the tracks, we would have theta for the angle of the pole, and then we have the first order derivatives X dot and theta dot. Unfortunately, this does not match our description of Markov decision processes, where I said that the state space should be finite. So what we do in practice, and we'll see that this can lead to issues, is we discretize the state space. The action space is very simple. We have two actions. We move the card either to the left or to the right. The initial state is chosen randomly according to some uniform distributions. The transition kernel is actually somewhat special here because the transitions in the card pole problem are deterministic. There's no stochasticity in there. They are governed by the laws of mechanics. And we additionally have a transition to some terminal state if we are either outside the feasible range or if the pole has irrevocably turned to one side or the other. And then finally, in this problem, we assume that we get unit rewards for every time period where we're still in the game, so as to find policies that balance the pole for as long as possible. Let's look at an example. I've implemented this problem actually. And in this implementation, what I've done is I have discretized the state space into 15 to the power 4 different states. Recall the state space here was 4-dimensional, but continuous. I had to transform it into a discrete state space. So for X, X dot, theta, and theta dot, I had 15 possible values, and that makes 15 to the power 4 states. What I show you on this slide is I show you only the X and the theta. I don't show you the first order derivatives. I've solved this problem using value iteration. Oh, this is where my computer decided to have enough. You see, nothing moves anymore. See? Let me try to see whether, all right. That's interesting. That has never happened before, but let me see. Let me try to restart my computer. Let's see, how do you, it doesn't even restart now. There we go, it does. Let's have a look. Maybe Markov decision processes are not that tractable after all. Should be fine, probably, hopefully it just... no, that's fine. It's just because it's starting. It hasn't yet. There we go. It's coming. All right. Quick reboot. Exactly. Let's see where it works now. Oh, this looks unusual, but let's see. All right, let's give it a try. Card pole example, second go. There we go. So I've implemented this policy. I have implemented value iteration to find the optimal policy. And you can see the policy in action here. I don't show you x dot and theta dot, but you can see the 15 states for x and theta. And as you can see, the policy does quite a good job in balancing the pole. But it doesn't work. It doesn't always work, and then it restarts here. Okay, and the policy keeps going like this. Great. The next topic is going to be LGKH. That is part of the reboot, apparently. Let's hope that the rest of the slides look better. It wasn't like that before. All right, the next topic is actually stochasticity and ambiguity. That looks more familiar to me. Okay, what I've done so far is I've just recapped some of the very well-known theory of Markov decision processes. Now I want to go into some of the research that Daniel, I, and many other people over the recent couple of years have done in that field by trying to apply distributional robust optimization in the context of Markov decision processes. So it turns out that while Markov decision processes quite faithfully model stochasticity in the system through the use of transition kernels, they do not per se account for ambiguity, which I interpret as uncertainty about the dynamics of the problem. And ambiguity, in my experience, arises for at least two reasons. The first one is modeling errors, and the second one is estimation errors. Let me discuss those in turn. In the card pull example, modeling errors occur primarily due to the discretization of the state space. Recall what I've done is in order to match my definition of Markov decision processes, I have discretized the state space into 15 to the power 4 different states. But I could have chosen less as well. Well, let me first tell you this. If I discretize them into 15 to the power 4 states, it turned out that the optimal policy was able to balance the pole for about 32 seconds on average. I could have discretized the state space into 10 to the power 4 states. Seems like a logical choice as well. But it turns out that in that case, the optimal policy would have performed really bad. It would have been able to balance the pole only for a couple of seconds. So those are modeling errors. That's a source of ambiguity where the dynamics that we capture in our Markov decision process somehow don't match the dynamics in the outside world. And if we take the optimal Markov decision process policy, apply it in the outside world, we will be disappointed. The second common source of ambiguity are estimation errors. In reality, we typically don't have the transition kernel P. What we at best have is some observations about how the Markov decision process behaved in the past. And those observations, we can use them to estimate P, but that doesn't give us exactly P. And that's a problem, these estimation errors. We know that they can be exacerbated by optimizing based on noisy estimates of quantities. Now, in our card pull example, we assume the dynamics are known because they follow the laws of mechanics, but what we could do is we could model a slight distribution shift. We could say that we learn our optimal policy in a setting where there's no wind, but then we apply our policy in a setting where there's a small amount of stochastic wind. You can think of it as nature pushing the cart to the left or right slightly. And again, it turns out that under the assumption of a small amount of stochastic wind, actually the optimal policy of my Markov decision process would perform really poorly. Now those effects of modeling and estimation errors, they are well known in the optimization community. And one of the paradigms that have been developed over the last 20, 30 years to combat those sources of ambiguity is distributionally robust optimization. And applied to the context of Markov decision processes, we would be solving what we call a robust Markov decision process. So the idea here is the following. We again try to choose a policy pi that maximizes the expected total discounted reward. But now we assume that the transition kernel P that governs those transitions is no longer known exactly, but rather it's adversarially chosen by nature from an ambiguity set script P. So in other words, we play a Zuckerberg leader-follower game against nature. We need to choose the best possible policy pi here and now. Nature observes our policy, chooses the worst transition kernel P from that ambiguity set, and then we get a reward based on that transition kernel. And we want to anticipate nature doing that and find the worst case optimal policy pi. So let's first go back to our two examples of modeling errors and estimation errors and see how a robust Markov decision process would fare under those circumstances. So what I do here is I have first a look at the case of modeling errors. Remember, now under modeling errors, we don't have 15 to the power 4 states anymore. We only have 10 to the power 4 states. That's our modeling error. And we see the nominal policy on top, the robust policy at the bottom. The robust policy also has the same discretization, and both policies are fed the same instances. And as you can see here, on the same instances, the robust policy does quite a bit better than the nominal policy. The nominal policy does very poorly, and the robust policy does not perform as well as before the nominal policy in the finely discretized state space, but it does better than the nominal policy over the coarse state space. Likewise, let's look at a case of a distribution shift, this wind that is being added. Now we again have 15 to the power 4 states, so we don't add the modeling error on top of it. But you'll see a bar here which shows us the direction and strength of the wind. Again, the nominal policy is on top and the robust policy is at the bottom. This is not a good day for my laptop somehow. The good thing about this is this was the last video that I wanted to show you, and there seems to be a correlation with videos today. So now a quick 2-minute break till I rebooted the computer. It's interesting. There must have been, it worked yesterday. That doesn't help you very much, but perhaps there was an update that didn't work well. The good thing is this time it reboots much more quickly. All right. Like we are, let's see, that's our well-known slide from before. All right, no more videos. So, the purpose of my talk so far was to try to show you that when we are interested in modeling problems and solving problems via Markov decision processes, ambiguity is something that we should be concerned about. And robust optimization is a potentially promising paradigm to combat the adverse issues of ambiguity. Now, assuming we buy into that, then there are at least two questions that we need to address. The first one being, how should we choose this ambiguity set script P? In principle, we can choose any set, but hopefully there is some kind of principled way of choosing that. And secondly, and clearly related, how do we find an optimal policy for a robust Markov decision process? I've shown you for Markov decision processes, we know we can use value iteration, policy iteration, modified policy iteration, linear programming. How can we get an optimal robust policy? All right, let's address those two questions in turn. The first one being, how can we choose the ambiguity set script P? And I would like to give you a high-level outline in one slide, and then I go into the details of this approach. So my proposal is the following one. We start with a structural ambiguity set. I call it script P0, which incorporates all the information that we have about the world prior to using any statistics. I will then intersect that with a data-driven ambiguity set that is reliant on a historical sample, a historical observation of the transitions of the Markov decision process, in such a way that hopefully the outcome will be the outcome of this intersection will be an ambiguity set that enjoys strict out-of-sample guarantees. All right, so let me start with the structural ambiguity set. As I mentioned, this can be chosen by us based on all the information that we have about the world. The more information we have, the better, because our estimation problem will become easier to solve. I will have to make the assumption for statistical reasons that the unknown true transition kernel is in the relative interior of my structural ambiguity set. What that means is I need to know which transitions in my Markov decision process happen with probability 1. The fortunate thing is that typically this is known from domain expertise. So in the simplest possible case, we may just know which transitions have probability 1, and all the other transitions can be anything between 0 and 1. But I might have more information as well that I can incorporate. For example, I might have a Markov decision process where some transitions are uncertain, but I know that they should have the same probabilities, whatever those probabilities are. If you think about a concrete example, let's say in predictive maintenance, we might have machines whose state deteriorates over time, and we don't know the rate at which the machine deteriorates, but we could assume that this rate is stationary over time. That would be the case of multiple transitions whose probabilities we don't know, but we can assume that those probabilities are the same. In that case, we wouldn't have psi1 and psi2 to estimate, but just one single psi in the simple example. All right, that's the structural ambiguity set. And I now want to intersect the structural ambiguity set with a data-driven ambiguity set. And what I assume here is, in some sense, a setting similar to off-policy optimization in reinforcement learning. The idea is, let me assume that I have available a state action history, S1, A1 up to Sn, An, that was generated by some known historical policy. So somebody has operated that Markov decision process in the past, probably not optimally, and I have taken notes of what happened with the MDP. And I want to use this history to reason about the unknown true transition kernel of my MDP. Now, if I were to give this task to a statistician, probably one of the first suggestions would be, well, look at the maximum likelihood estimator. The maximum likelihood estimator is the transition kernel P that maximizes this likelihood function here. And this likelihood function expresses the probability of observing exactly this state action history Hn if my true transition kernel was P. What a maximum likelihood estimator simply does is choose the transition kernel P under which the observed state action history has the highest probability of appearing. Now, maximum likelihood estimation would give us a point estimator of the transition kernel. But we want an ambiguity set. So it feels very natural to say, well, let's look at all the transition kernels P, whose likelihood, or in this case, the log likelihood, is almost as large as the log likelihood of the maximum likelihood estimator P star, modulo some constant delta. Okay? So we take somehow all the transition kernels P whose likelihood is almost as large as the likelihood of the maximum likelihood estimator, given the state action history Hn. Now, what can we say about this ambiguity set? Here's my proposal. Let's choose delta as the 1 minus beta quantile of some chi-square distribution whose degrees of freedom depend on the number of uncertain transition probabilities that we have to estimate. Beta is a quantity that we can choose. And let's assume that our historical policy is sufficiently diversified so that we visit every state infinitely often if the historical policy would become infinitely long. That we need because we want to make inference and we can't, the statistical tools that we use, we wouldn't be able to make inference if there were some states that we only visit 3 times ever. Then we can show that actually our ambiguity set Pn that we take is a confidence region for the unknown true transition kernel P0. In fact, P0 will be contained in our ambiguity set with probability 1 minus beta, where we can choose the beta. So if you want to be somewhat moderately conservative, you could choose beta equals 0.1. Then you have a 90% chance that the unknown true transition kernel is in our ambiguity set. If you are more conservative, you may want to choose beta equals 0.01. Why does that matter? Remember, in a robust MDP, we find a policy that performs best in view of the worst transition kernel in the ambiguity set. Now we have an ambiguity set that contains the unknown true transition kernel with high likelihood. So that gives us an out-of-sample guarantee. If we implement our policy in real life, then with high likelihood, we will obtain out-of-sample expected total discounted rewards that are at least as large as the in-sample expected total discounted reward when we solve the Markov decision process. Let's make a stronger assumption and assume that we also visit every state action pair infinitely often. So we probe every action with a positive probability. This can be relaxed, but the notation would become somewhat more cumbersome. Then it turns out that our ambiguity set, as the length of the observation history increases, gets smaller and smaller. And it actually converges in Hausdorff distance to a singleton set that only contains the unknown true transition kernel. And this convergence happens at a standard statistical rate of 1 over square root n. So in other words, you can think of this as a funnel. We have an observation history of a given length. We might have 100 state action pairs, 200, 400, 500, I don't know. But the longer the state action history is that we have, our ambiguity set becomes smaller and smaller. It contains the unknown true transition kernel with probability 1 minus beta. And eventually it kind of would just be a singleton set that contains P0. All right, so from a statistical perspective, this ambiguity set, in my view, is meaningful. But unfortunately, in Markov decision processes, two things need to come together. It's the statistical side and the optimization side. And it turns out that for ambiguity sets like the one that I've just described, the optimal policy for the robust MDP is no longer guaranteed to be stationary and deterministic. It may be randomized and history dependent, which was this most complicated policy class that we saw on the second slide. On top of that, just evaluating the expected total discounted reward, the worst case expected total discounted reward of a fixed stationary and deterministic policy is NP hard. So it's very likely to be a difficult problem. Because of that, people have looked at more structured classes of ambiguity sets. And probably the most popular class, which goes back to, I believe, the 70s in computer science, is the so-called class of SA rectangular ambiguity sets. The idea here is, let's not just look at any ambiguity set P, but let's only look at ambiguity sets P that are the cross product of many, many smaller ambiguity sets, one for every state action pair, such that nature can kind of freely choose the worst transition, the worst transition probabilities for each state action pair separately. It turns out that for SA rectangular ambiguity sets, we get all the nice features that we had in classical non-robust Markov decision processes. There's always an optimal policy that is stationary and deterministic, and the Bellman optimality principle continues to hold. So we can pretty much do everything we used to do, just the same way for robust MDPs. That sounds great, but there are some issues with SA rectangular ambiguity sets. And I try to show them here on a very stylized example. Imagine we have an MDP with 3 states only. We deterministically start in state 1, and we would like to end up in state 2, where we get a reward. We would like to avoid state 3, where we don't get a reward. There are 2 actions, action 1 and action 2, that we can choose in state 1. If we choose action 1, we end up in the desirable state with probability psi. If we choose action 2, we end up in the desirable state 2 with probability 1 minus psi. Unfortunately, we only know that psi is between 0 and 1. We don't know anything else. Can anybody imagine what would be the optimal policy that we can choose in this robust MDP here? Remember, it's a game. We need to make the decision. We need to choose our policy, nature, and afterwards choose the worst value of psi. It turns out here, the best choice that we would have is to randomize between actions 1 and 2 with equal probability. Because then, no matter what psi nature chooses, we would end up in the desirable state 2 with probability 1/2. That's the best we can do. Unfortunately, this is not the process that an SA rectangular robust MDP would model. Under the assumption of SA rectangularity, we would allow nature to choose different values of psi for the two actions. Think of it as psi 1 and psi 2 that can both be between 0 and 1. So under an SA rectangular robust MDP, actually nature can simply choose psi 1 equals to 0 and psi 2 equals to 1. And no matter what we do, we will never end up in the desirable state 2. Because of that, we have looked into broader classes of ambiguity sets that still kind of capture some of the desirable properties that we have from traditional Markov decision process theory in terms of tractability, but that are better in this, that are less conservative in their attempt to characterize robustness. And one such class is the class of S-rectangular ambiguity sets. So here the ambiguity set P is again a cross product of smaller ambiguity sets, but now just one ambiguity set for each state S rather than a separate one for each state action pair SA. And it turns out that under S-rectangular ambiguity sets, the Bellman optimality principle continues to hold. An optimal policy, there is always an optimal policy that is stationary. It doesn't need to be history dependent, but it can now potentially be randomized. This is exactly the case in this example here. This turns out to be an S-rectangular ambiguity set, and the optimal policy is indeed randomized. Okay, so we embark on this compromise of S-rectangular ambiguity sets, and then the question is, how can we find the optimal robust policy? How can we solve this robust MDP under S-rectangular ambiguity sets? Recall from classical Markov decision processes, like 2 of my talk, that one way to find the optimal policy in a non-robust MDP was via the Bellman optimality equations. We need to solve this system of nonlinear equations, and we did that via value iteration. Now, in the case of robust Markov decision processes with S-rectangular ambiguity sets, it turns out that we get a very similar set of Bellman optimality equations. I call them the robust Bellman equations. It almost looks the same. The only two differences are that now we need to take the worst case transition kernel of our marginal ambiguity set PS here. And instead of taking the maximum of all actions, we need to take the maximum of all randomized actions. The good thing is, this operator here is still a contraction mapping. So you can think of this as the robust Bellman operator. It's still a contraction mapping. And so we can use some kind of, so hopefully we can use that in order to find an optimal policy. So here's the robust Bellman operator. It takes as input a value function V. We need to compute this max-min problem for every state S to get a refined value function. And then we can use value iteration on this robust Bellman operator to get the optimal value function, and from that we can get the optimal policy. Yes? Here, why is there a PS? Or, you mean pi being conditional? Oh, why is it not pi S here? Yeah, absolutely. Sorry, that was just an abuse of notation. You're absolutely right. This here, think of this as pi given S. Thank you. That's right. So this is just a vector here that is for the state S. Absolutely. Okay, so long story short, this max-min problem we need to solve many, many times. Potentially millions of times. Because we need to solve it once for every state in order to do one iteration of value iteration. And we may want to do hundreds of iterations of value iteration. It turns out this is what we would call a robust optimization problem. And in the robust optimization world, we'll hear much more about this in the second part of the tutorial. We have developed ways using duality to solve this problem in polynomial time. Basically, we can dualize the inner minimization problem. That gives us a single maximization problem, and we can use interior point methods to solve this. In reality, this would be way too slow, because remember, we want to solve that millions of times, this problem. So the way the robust optimization community has embarked in when it comes to robust MDPs is we make assumptions about the shape of the ambiguity set PS in order to get much faster solutions to this max-min problem. And one such class that we have proposed are, we call them distance-constrained S-rectangular ambiguity sets, where basically the ambiguity set PS is a sum of divergences. Think of this as distances of discrete probability distributions, is upper bounded by some kappa. And I want to give you a flavor of those results. So what I want to do is I want to solve this problem, this max-min problem, quickly if PS is this set. How can we do that? So this is my robust Bellman operator. And the first thing to note here is that actually we can use the any minimax theorem to exchange the order of the maximum over my randomized actions and the minimum over the transition kernels P, the marginal transition kernels P. Why is that the case? Because these two will be convex sets, and the function is actually bi-affine and pi and P. So I can exchange the order. And now I can observe, after I've exchanged the order, I actually don't need to randomize over my actions A anymore. Because now, we're actually maximizing a function that is linear and pi inside. I would have not been allowed to do that before, when it was a max-min problem, but now that it's a min-max problem, I'm allowed to change the maximization over all randomized actions to the maximization of deterministic actions. Now this min-max problem looks simpler, but I still don't know how to solve it. So what I'll do is I'll solve it via bisection. I will have logarithmically many probing points theta, and I'll ask myself, is the optimal value of this min-max problem less than or equal to theta or not? Let's plug in our definition of the ambiguity set PS. It's this it's this divergence constraint here. And now, if we look at this problem from a bird's eye perspective, what we're really asking ourselves here is there a transition kernel P for which f of P is less than or equal to theta, while G of P, this blue box, is less than or equal to kappa? But that's the same as asking ourselves, is there a transition kernel P for which G of P is less than or equal to kappa, while f of P is less than or equal to theta? I just swapped the two things around. How does that help me? It helps me because now, in this new problem completely decomposes along the actions. If you look at this, I minimize here over the transition kernels. It's the a-fold cross product of a probability simplex. My objective function is linearly separable in the actions, and my constraint has to hold separately for each action. So I can actually write this problem, which optimizes simultaneously over A probability simplices, as a sum of smaller problems that optimize over one single probability simplex each. And this problem here has actually, in my view, quite a nice interpretation. It looks perhaps a little bit cumbersome, but what it really is it's a projection problem. So this problem here is nothing else than projecting the center of my ambiguity set P0 onto the intersection of the probability simplex with a single linear inequality constraint. And the projection happens with respect to the divergence D that we can choose. So this is now a very well-structured subproblem, and we can find very efficient ways based on bisection or sorting arguments to solve this subproblem for a variety of different divergences D. So let me summarize, and then I show you the results for some divergences. So we started out with these distance constrained S-rectangular ambiguity sets, and we said we need to compute the robust Bellman operator as quickly as we can, because we need to do that millions and millions of times. It turns out that solving the robust Bellman operator efficiently reduces to solving such a projection problem efficiently. That can be made formal. If we can solve the projection problem exactly in a certain amount of time, then the robust Bellman operator can be computed in that time. That's basically the bisection argument that I've shown you. And that works also if we can't solve the projection problem exactly. So we looked at different distance functions D. The Kullback-Leibler divergence, Burke entropy, variation distance, chi-square distance. I believe we had some other distances as well. And we implemented efficient ways to solve the projection problem. That turns out to be quite easy because it's really a very well-structured problem. And with that, we obtained runtimes for the robust Bellman operator that are either better than the previously known state of the art for those ambiguity sets, or where we have new guarantees where there were none before. And in fact, one thing is interesting to note here. What I've done is I took away the log epsilon term in the complexity estimate just to make it not too long. The complexity of computing a Bellman operator in a non-robust MDP, where we have no robustness at all, is S squared times A if there's no particular structure. And here our complexity is just bigger by one logarithmic factor. So what that means is we don't know whether our algorithms are optimal or not, but we're at most a log factor away from optimality, because solving a non-robust MDP is a special case of solving a robust MDP. Here are some numerical results. What I do is I compare the runtimes of the projection problem as well as of computing the entire robust Bellman operator, our algorithm in red versus MOSEC, which is a standard solver from the literature, in blue on KL divergence ambiguity set. We see here the ratio for solving the projection problem, the problem size in terms of state spaces on the x-axis. The runtime ratio is about a factor of 250 for the projection problem, and the runtime ratio for the overall robust Bellman operator keeps increasing, and already for very small problems with 300 states, we're about 1,000 times faster than MOSEC. So this really shows that developing specialized algorithms for robust MDPs really helps. It makes a difference between a problem that is essentially intractable to one that one can solve reasonably well. Okay. So far, I used robust value iteration. Remember from slide 3 of the talk that value iteration is one approach that is used to solve Markov decision processes, but it's not normally the most effective one. It turns out if you have a classical Markov decision process, probably the fastest way, at least as far as I know, is modified policy iteration from the standard approaches. So it seems natural to ask ourselves, can we do something similar in the case of robust MDPs as well? And so what we really want to do is we want to only from time to time evaluate this complex step here, which is a robust policy improvement where we maximize over our randomized actions and minimize over the worst case transition kernel. We want to interlace this expensive step with many policy evaluation steps where we don't improve our policy. That would be the goal. That's what makes modified policy iteration efficient. And interestingly, people have tried this for several decades, and for a long time, people came up with different algorithms, some of which have later been proven to be incorrect. For others, the convergence was in doubt. And to our best knowledge, the first successful attempt to robustify modified policy iteration was by Kaufman and Schäfer about 10 years ago. They have done that for SA rectangular ambiguity sets, but the same applies to S rectangular ambiguity sets. And literally what they do is what I just described. From time to time, they use a robust policy improvement step, which is the expensive operator. And they interlace it with many robust policy evaluation steps. That's the cheap operator. Now, robust modified policy iteration works very well for SA rectangular ambiguity sets. And that's what Kaufman and Schäfer were interested in. They didn't care about S rectangular ambiguity sets. When we implemented this for S rectangular ambiguity sets, all the theory goes through, but it turns out it was not doing that well. It was a little bit faster than robust value iteration, but not much. And the reason for that is that for S rectangular ambiguity sets, even this robust policy evaluation operator turns out to be quite costly still, because we need to minimize here over all the transition kernels across all actions. That turns out to be still quite a tricky problem. So here was our proposal about partial policy iteration. What we do is we proceed just like Kaufman and Schäfer. We have one complicated robust policy improvement step that we execute from time to time. But then we only execute a single robust Bellman evaluation operator. And then we iterate a couple of times with the worst case transition kernel, remember? Remember the robust policy evaluation here. We solve this problem once. We take the optimal P here, and then we just do a nominal policy evaluation on that worst case P. And we do that a couple of times. And that turns out to be really cheap, because it can be reformulated just as a non-robust MDP problem. And it turns out that one can still prove convergence of the overall thing, although using different arguments. And then when we combine the two, the robust value iteration that I've shown you from the previous slide, together with this idea of robust modified policy iteration, we call it partial policy iteration, we get another substantive speed up. So what we see here is in blue are the runtimes on different problem instances of robust value iteration, and in red, the runtimes of partial policy iteration. And you can see here the runtimes are maybe the improvement might be another factor 5 to 10 or something that multiplies on the factor of 1,200 or something from the previous algorithm. All right. I have a few minutes left, and I would like to change gears slightly now. So far, we talked about ambiguity and how robustness can help us to address the issues that ambiguities cause. Now, I would like to discuss some recent attempts, not just by us, but also by others, to extend Markov decision processes to large-scale systems. Of course, nowadays, when we think of large-scale problems and dynamics that are motivated by Markov decision processes, we often think about reinforcement learning for very good reasons. Reinforcement learning, I think, has been exceptionally successful in solving such complicated and large-scale problems. But oftentimes, reinforcement learning, to my understanding, exploits less of structure in problems. And oftentimes, large-scale problems have structure that we can exploit, and we can exploit them to get somewhat stronger convergence guarantees than the ones that are typically provided by reinforcement learning. So this part of my talk is actually motivated by a real-life problem that our medical team brought to my group during COVID times, and that was the issue of national patient prioritization. As many of you might know, in the UK, we have a huge backlog of patients that are waiting to be treated in hospitals. It is right now about 8 million patients that are waiting to be treated. And there's no way that we can see all those patients in time. So we have to prioritize. Between the estimated length of stay for different types of surgeries versus the benefits to life expectancy, etc. And that is a problem that the government is currently addressing, how to find such a patient prioritization strategy. And the question is, so the first question is, which patients should we prioritize? And then also, should those priorities change over the course of a year? So we have different priorities in summer when it's relatively calm in our hospitals versus winters when we fight the annual flu outbreak. So we tried to address this problem through Markov decision processes. And in particular, we modeled each of those, we had 10 million patients in our model, as a small Markov decision process. I show you a simplified version here, but it's not much bigger. In this picture here, the small clip arts show potential patient states. The arrows are stochastic transitions whose probabilities we estimate from real data. And then the annotations of the arcs are actions that trigger those transitions. So broadly speaking, each patient in our model will go through certain states or stages. First, they wait for treatment. Then they get admitted either as a routine appointment or as an emergency appointment. They get treated either in critical care or in general and acute care, or in a third state, which is they should have been in critical care according to their condition, but due to resource constraints, they are treated in general and acute care. These patients can randomly transition between those three states while they're treated at hospital. And then finally, eventually, they will be released from hospital. Hopefully healthy and well, but of course, this is not always the case. Okay? So we treat each patient in the UK that is waiting for treatment as such a Markov decision process. And then what we do is we piece together all those Markov decision processes into one single giant Markov decision process. That giant Markov decision process is going to have states that are vectors where each component of that state vector characterizes the state of a single patient. So these vectors will be 10 million dimensional. Likewise, we have actions that string together for each patient what we do with the patient. Do we admit the patient to hospital? Do we send her to general and acute care or critical care, etc.? We then make a conditional independence assumption, which means that conditional on the actions that we have chosen for the patients evolve independently, in which case we get the initial state distribution and the one-step dynamics from just multiplying the probabilities for the individual patients. And the patients are actually linked through resource constraints. The patients compete, in some sense, for the same limited resources, which are junior doctors, senior doctors, nurses, and different types of hospital beds. So that links the patient MDPs together in this large MDP. Now, this is, in some sense, a hopeless MDP to solve exactly, because, as I said, the state space is something like 15 states per patient to the power of 10 million. Now, in this MDP, again, I want to find a policy. Now, however, over a finite time horizon, we normally look at 1.5 years ahead of time, and there is no discounting here. But again, I want to maximize the expected total rewards, which are here a mixture of a combination of the years of life gained. So how much can we prolong the patient's life, subtracted by hospital costs that arise from the treatments. Okay. So I was mentioning before, this MDP is hopelessly large to solve exactly, but fortunately, the size of the MDP helps us in some way as well. And the way in which it helps us is that since we have so many patients, while each individual patient's evolution through the system is highly uncertain, at a population level, the dynamics become almost deterministic. Let me try to give you an idea why this is the case. Imagine a simple example where we're only interested in the initial state, and patients would be either a scheduled surgery or an emergency appointment with probability a half each. If we had a single patient, then there's a lot of uncertainty in the system, right? Because with probability 1/2, they might be a scheduled appointment, and with probability 1/2, they might be an emergency appointment. But if we increase the number of patients, we see that at the population level, actually the distribution converges essentially to a Dirac distribution at the probability of 1/2. This is, of course, just the law of large numbers. So what that allows us to do is to approximate our huge MDP well by a linear program, which I call the fluid linear program. Let me just briefly give you a flavor of this problem. So this is a linear program in the decision value sigma and pi. Think of sigma as our state and pi as the policy. In particular, sigma Ti of Si will tell us there is a second approximation that I wasn't telling you about yet, namely that we assume we could divide patients in this fluid approximation. Think of it as sigma Ti of Si, the percentage of the ith patient that in week T is in state Si. And think of pi Ti of SiAi as the percentage of sigma TISI that we apply action AI to. Then what our fluid linear program does is it maximizes the expected total rewards over all time periods and all patients, subject to our initial state distribution Q, the one-step dynamics of the system, which are governed by the transition probabilities P. We have our resource constraints from before, the junior doctors, senior doctors, nurses, etc. And we have another constraint that no patients are lost in the system. This is a linear program that scales linearly in the number of patients. It does no longer scale exponentially in the number of patients, which was the case for the Markov decision process. And as a result, we can solve this for 10 million patients, I think within 1.5 minutes on an open source solver. So this problem can actually be solved quite efficiently. But it's an approximation. So the natural question is, how good is that approximation? So the first thing one can show is it's actually a relaxation of the original weakly coupled Markov decision process. And then the main result is that actually this approximation allows us to construct a randomized policy for the original weakly coupled MDP. And the idea here is the following. Let me show you an example. Imagine we have an optimal policy sigma, an optimal solution sigma star pi star to our fluid linear program. And imagine for some patient I in some week T, that patient should be in general and acute care with probability 0.75 or 0.75, 75% of that patient should be in general and acute care. And imagine that our pi star from the fluid linear program is such that we should keep 0.5, 50% of that patient in general and acute care, and we should move 25% of that patient into critical care. Then what we do is we simply take the fractions 0.5 divided by 0.75 and 0.25 divided by 0.75. We take that as randomization probabilities with which we choose the actions, keep that patient in GA, or move that patient to critical care. So in other words, what we do is, in our fluid linear program, we have some kind of, we made the problem deterministic and we made it continuous. Now we get a randomized policy that tries to mimic what this fluid linear program does, and we want to implement that randomized policy in the original weakly coupled MDP. That thing with the 10 million, with the 15 to the power 10 million states. And it turns out that actually this randomized policy will perform very well. In particular, one can show that if we slightly modify, and we describe how, the resource availabilities in our fluid linear program, then this randomized policy is feasible with probability going to 1 very, very quickly. And the relative suboptimality to the unknown optimal policy in a weakly coupled MDP goes to 0 as the number of patients n increases. So in other words, somehow the fact that we look at a very large MDP really helps us to make the solution much easier. Not the exact solution, but an approximate solution that becomes more and more exact as the problem gets larger. We have implemented this in our case study. So our medical team at Imperial College gave us weekly updates on the number of COVID cases and estimates of the transition probabilities, etc. And we compared our policy, which comes on the next slide, against our best understanding of what the government has done. So as part of this team, there were some of the most senior government advisors actually during the pandemic. So we had a reasonably good idea of what was going on. And the government policy was like this. Every bar to the top here are routine appointments that we could still undertake during the pandemic. Every bar to the bottom here were cases that were supposed to go into emergency care, but that were sent away from hospital because of resource constraints. So they were either sent to field hospitals or they were sent home. And this is the policy that we obtain when we solve our fluid linear program. Not immediately obvious. It seems that we have a few less emergency deniers, but it turns out that this policy actually would be able to save 8.7% more life years. So that's quite a significant number across the UK. We would have, under the assumptions of our model, of course, we would have about 22% less emergency appointments, and we could schedule much more elective appointments. And we have tested those numbers. There were 2 papers. One was more a policy paper, which appeared in Nature Computational Science. And we really tried to look at various different scenarios of how the pandemic could have panned out back then. And under all of those scenarios, it turned out that this fluid policy seemed to work quite a bit better than what the government was doing at the time, which was maybe also not the most ambitious baseline, admittedly. And this brings me to the end of the talk. Here are some of the references that I used. Thank you very much for your attention. And if you have any questions, I think we might have just a little bit of time to answer those. Thank you.
Yep, any thanks?
Yes,
please.
Maybe I'll give you the microphone.
Oh, sure. In the last part of the first part of your talk, you show min-max equals to max-min, and that means there's a saddle point, and one generally uses an iterative algorithm for saddle points where you do min, and then max, min, and then max. Does that work in this case?
Thank you. That is a very sharp observation. That's right. So this relates, these days I'm nervous in moving any slides here, but let's see, hopefully. So the question was concerning the first part of this proof, where I exchanged the min with the max. And the suggestion was, well, when this holds, we have a saddle point problem. Can we use an iterative algorithm to solve the saddle point problem? And I'm not an expert in those algorithms, but to my best understanding, those are the first order methods that were suggested very recently by Julien Grand-Clément and collaborators, which are in the first row here. The complexity OL square S square A is from first order algorithms. What they do, if I recall it correctly, is they have from time to time a robust value iteration step, And then they have a couple of first-order steps for the saddle point problem. Interestingly, while one would expect first-order algorithms to work really well here, it's a large-scale problem. We don't need a very accurate solution. They turned out to be very slow in our implementation, possibly because L here is the iteration number. Somehow the way they solved the problem, and I'm not sure whether that's the best way to do so, but the iteration number enters their complexity estimate. And so after a couple of iterations, their approach became very slow. So at the moment, it's kind of more a proof of concept, but I don't think they are competitive at this stage.
Any other question?
Yes. Oh, perfect. Thank you.
So as I understood from all the ambiguity sets, you look at like a worst case estimate on where your transition kernel basically comes from.
Yeah.
Is there also a theory regarding that the transition kernel itself comes back from a probability distribution, which I think is also very natural when you think about like dynamic systems?
Yeah, thank you. There is indeed very little literature, but there is, where people essentially look at a second layer of robustness. So the idea there is that the transition kernel is itself a random object, and people look, I think, at all probability distributions within some Wasserstein ball there. So you're most welcome to send me an email, and I can give you those references as well. There are, like, I think 2-3 recent papers there. That's right.
Okay, I think that we have time for another quick question.
So, according to your presentation, the robust MDP, the optimal policy is a policy that maximizes the expected return, right? But for certain tasks or certain environments, this is not the case. For example, the gambling. We have the same kernel, or we have the same distribution, transition dynamics, but when you see when you look at that for 100 runs, 5 of them are really good, but 95 of them are really bad. The expected return is really good, but that's not what we want, right?
Yeah.
What do you think about this case?
Interesting. So if I understand you correctly, and please correct me if I don't, it is quite customary in Markov decision process to look at the expected total discounted reward. But of course, the expected value is risk neutral, and that does not always reflect the risk attitude of the decision maker, right? There are these standard examples. You can enter a lottery. You either win £1 million with probability 0.501, or you lose £1 million with probability 0.499. Would you prefer to enter that lottery or do nothing? According to the expected value, you should enter that lottery, but most people wouldn't. That's right. One can, in principle, look at one can, in principle, look at optimizing risk measures. One needs to be careful, though, that when one optimizes over risk measures instead of the expected value, that the Bellman optimality principle continues to hold. That is the case for certain classes of nested risk measures. So there is a paper by, I think, Andrei Rushinsky that has investigated when that is the case. Interestingly, distributionally robust optimization often has a dual interpretation as a coherent risk measure. So that is something where I'm not sure that people have looked into that carefully, but it would be interesting to see whether when we solve robust Markov decision processes, to what degree we're actually solving some over a particular class of risk measures in the dual sense. It's, to my understanding at the moment, quite possibly an interesting open question. Pleasure.
Okay. I think it's coffee time now, so many thanks once again.
Thank you very much. Thank you.
Welcome for your superb presentation.
Thank you.
And we are looking forward to the second part, but coffee break now.